So we're asked which of these statements must be correct about organic isomers. So firstly, they have the same molecular formulae, then their physical properties are very similar, and that they have different structural formulae. So firstly, we know that isomer is quite a broad term, so let's think about what we mean when we say isomer. So what are the two main types? We have structural isomers and stereoisomers, and we know that these have some subcategories. So what are the three kinds of structural isomer? We have the chain length, position, or functional group isomers. And with stereoisomers, we have EZ isomerism and optical isomerism. So now let's look at these statements. So do they have the same molecular formulae? Well, we know that molecular formula is just something like C3H6O, which just gives the number of atoms in the molecule. And does this differ between the isomers? So we know structural isomers differ only in the structure, and stereoisomers differ in the spatial arrangement of atoms. So regardless of this, they're still going to have the same number of each atom. That's what makes them isomers of each other. So this is correct. They always have the same molecular formulae. Next, what about their physical properties? Are these always very similar? Well, let's take a think. What about these chain isomers? So, for example, we can have hexane, or similarly, just by changing the arrangement of the carbon chain, we can have this 2,2-dimethyl butane. Do these have similar physical properties? Well, we know that with these long chain-like hydrocarbons, we have a higher boiling point because they can pack together more closely and they have stronger intermolecular forces. But with the more branched ones, the reverse is true. They're forced apart by these bulky groups, and they have a lower boiling point because of the weaker intermolecular forces. So boiling point's a good example of a physical property, and we know that these aren't similar at all, so the second one is wrong because it's not always correct. And finally, what about the structural formulae? Well, what is a structural formula? So this is a diagram that represents the 3D arrangement of atoms in a molecule without necessarily drawing all the bonds like in the displayed formula. And so why don't we think about the most similar looking isomers, which is the optical isomers. We know that these only differ by being non-superimposable mirror images of each other. So we have this chiral center, for example, in butanediol, and we know if we reflect this in a mirror, we get a different molecule where these bonds have just switched places. So these are as similar as it gets for isomers, but do they have different structural formulae? Well, yes they do, because that's what I've drawn here. We've displayed the bonds that define the structure. That's these OH and H bonds. And so we can see that these aren't the same, and therefore they have different structural formulae. And so this one is always correct. Since if they had the same structural formulae, then they wouldn't be isomers. They'd just be the same molecule. So our final answer is 1 and 3 are correct, which corresponds to E on the question paper.